Okay, so today in this chapter we'll define a quantity called angular momentum, okay, and we'll show you Newton's second law for rotational motion. Okay, so this was linear momentum, which was a vector, and this was Newton's second law, okay, in terms of momentum. So the net force acting on a system, okay, was equal to rate of change of linear momentum of the system, okay. And the parallel of linear momentum when for rotational motion is angular momentum, and that's what we'll introduce, okay. And you will see Newton's second law is net torque acting on a system is equal to rate of change of angular momentum. Okay. Now, in this week, some of you have done this lab. You saw that when the net force acting on a system is zero, okay, the momentum of the system is constant, is conserved. Okay, so you saw that we did an experiment in collisions, and you saw that the total momentum of the system before the collision was equal to, so when net force is zero, is constant, okay. So momentum before the collision was equal to momentum after the collision for a system, and that's the lab you did, okay. And at the end of this chapter, you'll see that when the net torque acting on a system is zero, the angular momentum of the system remains constant, okay. And we'll see spectacular examples of that. Okay, so in nature, when random forces act, their net torque is generally zero, okay? And we'll calculate torques about axes passing through the center of mass, and you'll see some spectacular examples of this, okay? So we'll see where net torque acting on the system is zero and angular momentum will be constant, okay? All right, so what we are doing is Newton's second law. This will be our goal. Yep.
What's that weird P-looking sign?
What P looking sign?
The one that does that one.
This one? This one?
Maybe somewhere on top of that.
Yeah, this one makes sense. That means momentum?
Yeah, P is momentum. This is little p. It is P, it's not P looking. I guess you slept through the last chapter. All right, so now we will talk about the second law, Newton's second law for rotational motion. But before we do that, we'll consider rolling motion. Okay. This is important in our life. I mean, when you drive your car, your wheels are rolling without slipping. Okay, so let's look at that first. Okay. All right. So I'm recording this, but I guess the people who are listening to the recording won't be able to see this. So here's the rolling motion. This is rolling without slipping. And so if this is rolling with slipping. Okay? Of course, you don't want that because then you're just wasting gas. Okay? What you want is this. Okay? And it turns out we'll show you this. Rolling is pure rotation plus pure translation. Okay? So that's what we're going to show you. Did you guys understand that? So rolling motion without slipping is pure rotation plus pure translation. Okay. Now also here's what that diagram is. Okay. So if this is a wheel, you put a light bulb here on the rim. Okay. And if this object rolls, this wheel rolls at constant velocity, that light will go on a cycloid. The path traced by the light bulb will be a cycloid. So light on the rim of a wheel rolling at constant velocity, that's a cycloid. Okay? And this is, of course, the axis is the only point that goes in a straight line. Okay? All right, so rolling motion, rolling without slipping is a combination of rotation and translation. It's a sum of rotation and translation. Okay, so a pure translation, in pure translation, every point in the wheel is moving at the same speed. Okay, so that's pure translation. In pure rotation, opposite points, okay, equidistant points from the axis of rotation are going in opposite direction, have opposite velocity. Okay? So the further out you are, the faster you're moving. So closer you are, your velocity is smaller. Okay? Now, pure rolling, all you do is you just add these two velocities. You add these two. So this point, when a wheel rolls, this point is at rest. That's the only point that's at rest momentarily. Okay, so that's the point that is on the road. Okay, yeah, that the point, the wheel touching the ground, that point is at rest. Okay, this point is going the fastest. It's this velocity plus this velocity. So if your wheel was going at 5 miles an hour, this this point is going at 10 miles an hour, 5 miles an hour. This point is going at 0 miles an hour. Okay? So rolling motion is pure translation plus pure rotation. Okay? All right. All right, so now let's look at a wheel that is rolling without slipping. So you can mark a line on the wheel, and when you say the wheel has rotated through an angle theta, when this line comes to the bottom, then the wheel has rotated through an angle theta, okay? And the wheel has moved this distance. It has rolled that distance, okay? And that distance S is R times theta. Yep. What are the units of theta? Radians. Okay, whenever you're relating linear quantities to angular quantities, that has it's got to be always in radians. Okay? All right, and then you can take the time derivative of that. You take the time derivative of that, that's the speed of the wheel, okay, and that's the velocity of the center of mass of the wheel. R is constant, and d theta by dt is omega, the angular velocity. So the angular velocity of the wheel is related to the velocity of the car. Okay, and we've said this before. Your engine can provide you with a maximum angular velocity. So for the same engine, if you want to go faster, all you do is put in bigger wheels on the car. Okay? Wheels with a greater radius. Yep.
Is that velocity like towards like the center point, like how far it's moving linear?
The velocity of the center of mass. Yep.
Oh,
And since your car is attached to that wheel, that's the velocity of your car. Yep. If your velocity is changing, the center of mass velocity is changing, that's the acceleration, your acceleration, and that's equal to d omega by dt. So the acceleration, the angular acceleration of the wheel. Yep. So the acceleration of the center of mass is equal to r times the angular acceleration. Okay, so if you have a bigger wheel, your final velocity will be greater, and your linear acceleration is also greater. Okay, so you can go 0 to 60 faster as well. All right, so when a wheel rolls, here's the instantaneous picture of the velocities of various points. There's the velocity of the center of mass, or that's the axle, that's the velocity of the axle. This point is going in that direction. This point has the greatest speed. This point is going like that there. Okay, this is the only point that is momentarily at rest. Okay. Now, so the kinetic energy of the wheel is this kinetic energy plus this kinetic energy plus this, and so on. Okay, if you add all those up, it turns out that the kinetic energy, C, is written as, this is a pure rotational kinetic energy. That's the moment of inertia about the center of mass, so pure rotational kinetic energy, and this is pure translational kinetic energy. Okay. So this is rotational kinetic energy, and this is translational kinetic energy. Okay. So, like we keep saying, rolling is pure rotation plus pure translation. Okay. All right, so when a wheel is rolling without slipping, when it's not slipping, okay, so here's what's happening. Okay, what is your car engine trying to do? It's trying to spin this wheel faster and faster, okay? And if this point is not moving, well, so if you held the car up, if the car was not touching the road, all that the wheel will do is just spin. Soon as the car comes in contact with the road, this point is not slipping anymore. Okay, so if it's not moving, why is it not moving? It's because of the friction that the road applies on the wheel. And since that point is not moving, that's a static friction force. And so that's what makes your car accelerate.
So it's only static friction force?
It's a static friction force. All right? So the static friction force is what gives you the acceleration. So I don't know if you guys watch drag racing, the quarter mile thing that those cars go on. So what is it that they do first? I'm sorry? Yeah, they burn out. What are they doing? They're heating their tires, so the maximum static friction forces, they're increasing mu s. Okay, when the tires are hot and sticky, mu s is increasing, and so Fs increases, the maximum Fs increases, and Fs increases, and your acceleration is greater. Okay, so that's what they're doing. All right. So what this is showing you is the following. So if you have a wheel that is rolling down a ramp without slipping, it's giving you the acceleration of this wheel, of the center of mass. Okay, now before we look at this expression, and by the way, this expression here is where it comes from. There's the mg sine theta, is that's the weight of the wheel. This is mg sine theta. That's that. There is the static friction force that's preventing it from slipping, and so there is the net force, and that's equal to mass times acceleration. But anyway, so they've solved this here. It's solved, and once you solve it, you can solve for the acceleration of the center of mass of the wheel. Now we'll look at this closely. Okay. Now, if you had an ice cube that was sliding down on a frictionless surface, the acceleration of the ice cube would be g sine theta. Okay? A would be g sine theta. Okay, so the acceleration of this wheel that is rolling down is g sine theta. It's exactly the same, except that it's smaller by that factor. And greater the moment of inertia of the wheel, smaller the acceleration. Okay? So you take any wheel and let it roll down a thing, and let an ice cube slide down the same incline, the ice cube will get to the bottom faster. Okay? So anything sliding frictionlessly will get there faster. Okay? All right. So again, greater the moment of inertia, smaller the acceleration, smaller the rate at which the speed builds up. Okay? Moment of inertia, so when is moment of inertia greater? So for an object, if the mass is spread out further from the axis of rotation, then the moment of inertia is greater. Okay? So here are three wheels, they have the same mass. I mean, this is a sphere. They have the same mass and same radius. So you see that there's the axis of rotation. This is the axis of rotation for all of them. Okay, this is the axis. So this guy has mass spread out further from the axis of rotation. His moment of inertia is greater than his moment of inertia. So this guy's acceleration will be smaller than this guy's acceleration. Okay? So between these two guys, if their masses are the same and the radius are the same, this guy will be second, this guy will be first. Okay? The moment of inertia of this guy, I is the moment of inertia of this guy is 1/2 mr squared. You can look this up in tables. The moment of inertia of this guy of a wheel is 2/3 mr squared. Okay, so the moment of inertia of this guy is greater than this guy, so he will be slower than him. Okay, and you saw that this guy is slower than him, so this guy is first. Now between these two guys, the moment of inertia of this guy is I is 1/2 m r inside radius plus square plus r outside radius square. Okay. In this formula, that's the outside radius. Okay, so if this guy happens to be greater than 2/3 mr squared, that for the wheel, then he'll be behind the wheel. Okay. So it just depends on what his moment of inertia, this guy's moment of inertia, I for the ring is between 1/2 mr squared and mr squared. Okay. So when his moment of inertia is greater than 2/3 mr squared, then he will be behind that guy. Okay. Anyway, the point is, greater your moment of inertia, smaller your acceleration. Okay. Anything rolling down will get to the bottom slower than an ice cube sliding down. Okay. This just gives you the final velocity at the bottom of the hill. Okay. All right, so now what we're going to do is prepare to give you Newton's second law for rotational motion. What is Newton's second law for rotational motion? What is the formula? What is Newton's second law for linear motion? I'm sorry? Okay, so that's the baby version. What is the real version? That's right. Okay, F equal to dP by dt. Okay, so this is for linear motion, and for rotational motion, that forces get replaced by torques, and linear momentum gets replaced by angular momentum, d by dt of L. Okay, so we are building towards this equation. Okay, so that's the goal of this chapter, to show you Newton's second law for rotational motion. Okay. All right, so here's an object, and if you apply a force on this object at this point, and it's free to rotate about that axis, the torque of this force is R cross F. The torque of that force is R cross F. Okay, so every force has a torque associated with it. Okay, and the torque depends on the point of application. So that same force applied over there will have a different torque. Okay, so a given okay, so you could apply this force over here. You could apply that vector has not changed. The force can be applied at different points, and the force can be the same, but its effect to rotate the object is different. Okay, so the torque will be different. Okay, so the torque of a force is R cross F. Okay, where R is the vector pointing from the axis of rotation, or the point about which you're calculating the torque, to the point of application of the force. Okay, and this force, it's this object is can rotate about that axis will give the object a counterclockwise rotation. Okay. Angular momentum, and again, torque is a vector. Okay. What does that mean?
His direction.
It's got magnitude and direction. What that also means is if you have several torques acting on the object, the total torque is just the sum of all those torques. Okay? You can add them. It's a vector sum. Okay? All right. Angular momentum denoted by L, that's also a vector. Okay? So if this point is moving at a velocity with a velocity v, its linear momentum is mv. Okay? And the angular momentum of that point about that axis of rotation is r cross p. Okay? So the angular momentum is r cross p. It's just defined just like the torque. Torque is r cross f, and angular momentum is r cross p. Okay. And now we'll introduce Newton's second law. This is for a very simple case. So here's a point particle, okay, and it's traveling in this direction. So let's say this could be a planet, okay, and we're going to calculate the torques and angular momentum about that point. All right, so the force, let's say there's a force acting on this particle. What does Mr. Newton say? Force is dp by dt, okay. That force is going to change the momentum of this particle. And so here you have this equation. So what you can do is, when you have an equation, you hit this equation with a hammer, you have to hit this guy with the same hammer. Okay? So what we'll do is, we'll take R and do a cross product there. And so you have to do the same thing here. R cross P. Okay? What is this? That is the torque acting on this guy about this point. So that's the torque acting on this guy. And the torque is R cross that. Now, we'll use a little trick. Do you guys remember what is A cross A? What's the cross product of a vector with itself? It's 0. Okay. So, what is this guy? That's P cross P. That is 0. So you can add 0 vector to any vector and it doesn't change the value of the vector. Okay. So dr by dt, this is P over m cross P, this is 0. Okay. So what we can do is, what we are doing is, okay, so this guy, d by dt is dt of r cross p. Using the chain rule is dr by dt cross p plus r cross dp by dt. What was this? This was p over m cross p. This was 0. So you're free to add this to that. So this guy, which was that term, can be replaced by that term. Okay? Because this was 0. And that's what we've done. So we've replaced this by that. So the net torque is equal to that. But this guy is angular momentum. So there is your Newton's second law. So net torque acting on the object is equal to dl by dt, rate of change of angular momentum. Okay? So we proved this for a very simple case, but it's generally true. Okay? So what I want you to remember for the rest of your life is the following. This is Newton's second law for linear motion. And this is Newton's second law for angular motion. Okay? So Newton's second law for linear motion says the net force acting on an object is time rate of change of momentum of the object. And this can be applied to a single particle. It can be applied to a system of particles. Similarly, okay, when a force makes an object rotate, the net torque acting on the object is equal to rate of change of angular momentum of the object. Okay? That's the punchline in this chapter. Okay? All right, now we'll apply that to some situations that we encounter in real life. Okay, so for a system of particles, if one particle has angular momentum L1, okay, so these are the angular momenta of various particles. The total angular momentum of the system is just the vector sum of all of them. Okay? If there's a torque acting on each particle, the net torque acting on the system is just the sum of those torques. Okay? So this formula applies to a single particle as well as a system of particles. That would be the net torque acting on the system, and that's the net angular momentum of the system. Okay? All right. I'm going to speed up a little. Okay, so the net torque acting on a system is torque due to internal forces plus torque due to external forces. The torque due to internal forces is always zero. Okay, because internal forces, for every force there's an equal and opposite reaction force, and they give you a net torque of zero. So the net torque acting on a system is only due to external forces. Okay, and this is interesting to us because let's say when random forces act on an object, or when you throw a ball and stuff like that, there's drag forces acting on the object, and the torques of those drag forces are always zero. Gravity acts at the center of mass, so if you're calculating torque about an axis passing through the center of mass, that external torque will be zero. So if an external torque acting on an object is zero, then its angular momentum will be constant. So if this is zero, this L will be constant. All right, and so we'll see some spectacular examples of that. Okay. Okay, net torque acting on an object is dl by dt. Okay, so this relationship between torque and angular momentum is independent of the choice of the origin. So what the statement is saying is each of these guys depends on what point you calculate the torque about. But this equation is so R depends on this choice, and R. Okay, so if you calculate the torque about this point, for the same force, torque changes, but then you calculate the angular momentum about the same point, and it correspondingly changes, and so this equation will remain valid. Okay? Okay. And that needs to be true for a law to be, for something to be a law of physics. It can't depend on the coordinate system, on the choice of the coordinate system. Okay, so that's a statement independent of the choice of coordinate system or the choice of origin. All right, so for an axis passing through the center of mass, net external torque acting on a system equals the time rate of change of angular momentum regardless of the motion of the center of mass. Okay, so again, we won't worry about all of those. What this statement is saying is for an axis passing through the center of mass, no matter what is happening to the center of mass, whether it's accelerating or not, this is valid. External torque is equal to dl by dt. Okay. Again, so this is our Newton's second law for rotational motion. Okay. So we will look at examples like this. Okay. All right. So here's a simple case for a particle moving in a circle. The angular momentum, magnitude of the angular momentum is mvr, so linear momentum times r. Okay. So for a planet going around in the solar system, its angular momentum is mvr. For a rigid object, okay, so here's what we're going to do next. So here was the case for Here was Newton's second law for linear motion. When did this reduce to F equal to ma? When does it reduce to F equal to ma? When the mass is constant. This is equal to d by dt of mv, okay, which is dm by dt times v plus mdv by dt. Okay, so when you're driving your car, the mass of your car is not changing much. It is changing because as you burn gasoline, it's reducing a little, but negligible. So most of the time we are able to throw away this term, and that's equal to mass times acceleration. That's when it reduces that. Okay, but when Elon Musk is playing, his rockets, the mass changed by 90%. Then you can't ignore this. Okay. All right. So there are similar situations. So torque is dL by dt, and so this will reduce to I times alpha when the moment of inertia of the object is not changing. Okay? So for a rigid object, the moment of inertia of an object won't change. But there are situations when the moment of inertia of an object changes. Okay, so for this system, the moment of inertia changes. Okay, and then you can't then torque is not equal to I times alpha. Okay, torque is equal to dL by dt. Okay. All right, so just keep that in mind. Okay. So that's what we're introducing. Okay, so just like when the mass doesn't change, Newton's second law reduces to F equal to ma. Just like that, for an object, when the moment of inertia does not change, torque will reduce to I times alpha. Okay? All right, so keep that in mind. So I'm going to show you the demonstration, but since I'm recording this, I'll just I'll go over the slides and then I'll show you the demonstrations at the end. Okay. You guys have all played with a top. Okay. If the top is spinning, there's the angular momentum. Again, you use your right hand. You point your fingers in the direction of rotation, and the angular momentum points in the direction of the thumb. Okay, so if you're using your right hand, your fingers pointing in that direction, and your angular momentum points like that. Okay. Here is the force of gravity acting on the top, and what is this trying to do? It's trying to topple this torque. It's trying to topple the top. Okay, so this force, and if you calculate the torque of this force, about that point, there's a normal force that'll have zero torque. This torque will be like in that direction. And what does the equation tell you? Torque is equal to dL by dt, or change in angular momentum over time. Okay. So change in angular momentum will be in the same direction as torque. So if the torque is in that direction, angular momentum will change in this direction. Okay, in the same direction. Okay, so what ends up happening is the top precesses. Okay. So if the top were spinning straight up, then it won't precess. But soon as it tilts over, it starts precessing. Okay. And you guys have all seen this, and I'll show this to you in a little while. Okay, so a spinning top precesses. It turns out that the faster the top is spinning, the slower it will precess. Do you guys know what I'm talking about? Okay. So a spinning top will precess. Okay. Yeah. So here is the axis of the top describing a cone. Okay. So here we are showing the same thing with the bicycle wheels. So when the bicycle wheel is spinning, if you have a bicycle wheel spinning, this bicycle wheel will precess. Okay. And capital omega is the precession frequency, the rate at which it's spinning, and that is much smaller than this angular velocity of the wheel. Okay. So the precession frequency is given by this formula. It's mgr, mg is the weight of the wheel, and r is that distance, divided by the angular momentum, I times omega. Okay, so the precession frequency is much smaller than the angular velocity. And again, I'll show this to you in a second, but let me get through. Okay, so yes, let's make sure we understand this, because I'll show you a very spectacular application of this. Okay, so if you have a spinning top, the force of gravity is trying to topple it, but if the top is not spinning, then it'll just topple over. But if the top is spinning, instead the same force will make the top precess. So did you guys understand that? If the top were not spinning, this force would just topple the top over. But if it's spinning now, the same force is making it precess. Okay, so we'll see that. All right, so here's a fun experiment you can do with your cat if you have one. Okay. Here's Newton's second law, and you can watch this YouTube video. Okay, so external torque acting on a system is equal to rate of change of angular momentum. Okay, so you can grab hold of your cat by its feet and you can drop it. Okay. So when you just drop it, its angular momentum is 0. Okay, so here's a cat with its feet in the air. You dropped it, its angular momentum is 0, and it'll always land on its feet. So what's going on? And apparently the limiting distance is 3 feet. Okay. So what happens, so the angular momentum is 0. Well, it landed with its feet. It seems like the cat has turned, so the angular momentum was not 0. Well, the external torque acting on the system was 0. This was 0. So the final angular momentum has to be 0 as well. So what is happening is the following. Okay, what the cat does is it turns its rear body along with the tail. If this is rotating in this direction, the front of the cat rotates in the opposite direction. Okay, and the total angular momentum remains 0 through the entire fall. And it's able to make itself land on the feet. Okay. And we actually, so this is not silly. We use this to turn satellites, and we'll come to that in a little bit. Okay, so this is. So here's another application. All right, so this relative velocity is when you throw the football forward, that's the wind velocity of the wind. Okay, why do we throw the football with a spin? What's that? Oh, no. So you throw the football with a spin when you give, so what this is this is a football thrown in the forward direction with a spin like this. So the football is spinning like that. Okay, and so again, use your right hand, point your fingers in the direction of the spin, and your thumb points in the direction of the angular momentum. Okay, so there's the angular momentum of the football pointing in that direction. Okay, like I said, when the wind blows, the torque of the wind, any random force applied, this is 0. So dl by dt is 0. Okay, so if you throw a spinning football, the L is constant, so the spin will point in the same direction. So if the wind is blowing like this, see, the face of the football is the same, and so the drag force is constant. And you have a supercomputer attached to your shoulders. This is a supercomputer. So as long as this guy doesn't wobble, and even if it's windy, you're able to calculate the drag forces, and you can calculate where the football will end up. And you'll catch it. But if the football wobbles, then the drag forces change, and this supercomputer is not able to calculate where it will land. Okay. So that's why you throw the football with a spin. Okay. If you want to see a great example of this, go throw a frisbee on the beach on a windy day. When you throw a frisbee, when the frisbee is rotating like that, so the angular momentum will be pointing downwards, okay? And no matter how windy it is, it'll maintain its orientation. Okay. So here's a system. Again, L is external. There's the force of gravity and the normal force, and they all pass through the center of mass. So if you're calculating the torques of these forces, the torques of these forces are 0. External force torques are 0. L is constant. Okay. So as this system spins, the angular momentum is constant. So right now, the moment of inertia of this system about that axis is larger because some of the mass is further from the axis of rotation. And soon as that mass gets closer to the axis of rotation, I decreases. So I is smaller here, I is larger here for the same system. And since L is constant, L is I times omega. Okay, so if I decreases, omega increases. Okay. So you start off a spin, you start a spin with your arms outstretched, and when you bring your arms in, you'll spin faster. Okay. Now, for this system, you're able to change your moment of inertia maybe by 20% or so. And so your angular velocity can increase by 20-30%, okay? Or maybe let's say 50%. But we'll see examples in astrophysics where this could be a star, and at the end of the star's life, so for instance, the sun is rotating at about 1 revolution per month. And if the sun cannot become a neutron star, but if something can become a neutron star, a sun, let's say, 3 times as massive, could become a neutron star. Its radius can decrease by a factor of 100,000. So that thing can spin much faster. So a star, let's say, that was spinning like 1 revolution per month can revolve 1,000 revolutions per second. Okay. And here's something spectacular. The person who discovered those neutron stars, they're called pulsars, will be giving a talk at Embry-Riddle in January. She should have won the Nobel Prize, but back in the day, she got stiffed. But anyway, so all right, so here's another example. Okay, so let's say here's a merry-go-round that's spinning. What do you think will happen if this guy walks towards the center, towards the axis of rotation? It'll spin faster, exactly like this. Okay, what you're doing is you're reducing the moment of inertia. You're reducing the moment of inertia, and you're increasing the angular velocity. Okay. I'll show this to you in a second. Okay, so let's say, okay, if you answer this, so you get only one shot at it. Okay, you'll get a donut. Okay, so here's a bicycle wheel. We'll give it a spin and hand it to this person. Okay, this person is at rest. Okay. And the bicycle wheel again, use your right hand. Your fingers point in the direction of the spin. Your thumb gives you the direction of the angular momentum. So here is the angular momentum. Okay. So this angular momentum of this system is that. And then what we'll do is we'll ask this person, so here's the person, we'll ask the person to flip the wheel. Yeah. there's no the force of gravity, the torque of force of gravity and normal forces are 0. External torque on this system is 0. So what did we say? L has to be constant. Initial L should equal final L. You guys understand? But here's the wheel that the angular momentum is pointing up, and you flipped it and it's pointing down now. It doesn't appear to be constant to me. What needs to happen? Did you guys understand that?
Can you see that last part again?
All right, so the external torque on the system is 0. Here's Newton's second law. This guy is 0, this is 0, L is constant. That is, initial value of L is equal to final value of L. Here's the initial value of the system. Okay, so let's say this is plus 30 units. And she flips the wheel and now it's become minus 30 units. That's not equal to that. So here's what will happen. Anybody for a donut? No. Okay, so you will see she will start spinning in that direction. Yeah, that's right. What is right? Okay. She'll have a unit of 60 units. Did you guys understand that? Yeah, no. It just blows your mind. Well, I'll show that to you. No, save it. There's no way to understand that. I'll show that to you in a second. This is so you guys thought that you just learned this thing, but you guys know this law intuitively. Okay. So here's the deal. Okay, again, conservation of angular momentum. Okay. So you guys have seen high divers, and what this person does is they push off initially. Okay. They push off. There's the weight acting, and so initially they give themselves there's a torque acting on them, and they give themselves an angular momentum. And so now, once they're on a parabolic trajectory, for the entire motion, the angular momentum is constant. Okay? Now, there are some diving contests where you have to spin 2 times before you hit the water. And there are contests where you have to spin 5 times before you hit water. I just made that number up, but different number of times. Okay? You're jumping from the same platform. You gave yourself a given angular momentum. So how do you control how many times you spin?
How fast you keep your legs in?
I'm sorry?
How fast you keep your legs in?
Yes, so what you do is, so you have a given amount of angular momentum. Okay. If you want to spin more, you reduce your angular momentum more. Okay. And the longer you've reduced it, the greater amount you've spun before you hit the water. Okay. So you are utilizing this constancy of this. So the greater amount you crunch up, the more you'll spin, and you can turn how many ever times you want and then hit the water. Okay. And when you don't want to spin anymore, you just straighten yourself up. Okay. I mean, even at this moment, just before you enter, you're spinning, but the goal is to enter the water straight. Okay. And then once you're in the water, that'll stop your spin. Okay. All right. So all this, you learn to do the following. Okay, so here's a satellite up there 500 miles above the surface of the Earth. And okay, so what the satellite is doing is bouncing TV signals off for you. And let's say some piece of debris hit it, and the satellite now is turned that way. Okay? I'm just making this example up, but let's say it's now off kilter now. Now, what has it become? It's become a 200 million piece of junk is what it's become. So to make this useful, you got to turn it like that. Okay, and here's what you can do. So here are gyroscopes that they put on the satellite. You turn the gyroscope this way and the satellite will turn that way. Once it straightens out, you stop the gyro and the satellite will stop. Okay? So you can have 3 gyros to make a satellite turn any way you want. Okay? Okay, so angular momentum turns out to be a fundamental quantity. What that means is, so in the universe there are about 10 to the 80 protons and 10 to the 80 electrons. And here's the amazing part. Well, that's a huge number, by the way. Every electron is spinning at the same rate. And the angular momentum, whenever something spins, it has angular momentum. The angular momentum of every electron is 1/2 h bar. The angular momentum of every proton is 1/2 h bar. Okay. So it turns out that everything that you see and touch are made by these guys. This is an up quark, down quark. This is a neutrino. This is an electron. Okay. Everything in the universe that is normal matter is just made of these 3 guys. Okay. It's these 3 guys, up, down, and the electron. And all of them have a spin of 1/2. Okay. It turns out in nature there are these guys. This is charm quark top, strange bottom. But these guys are heavier and they decay. Okay. So they don't live too long. So they all decay to that. These are the guys that mediate forces. These guys, these are force carriers. They have integer spins. Okay. H bar spins, in integer spins. Okay, 1 H bar or 2 H bar and stuff like that. Okay, the photon is 1 H bar. All right, these guys mediate the weak force. This guy mediates the strong force. This guy mediates the electromagnetic force. Okay. These guys decay into these guys. Okay. Even the structure of the atom. Okay, so a planet, for instance, can go around at any radius. Okay, so here's the sun. You can put a planet at this radius, at this radius, at that radius. So you can put the planet at any radius. Okay, now I'm loosely speaking, but anyway. On the other hand, an electron around a nucleus cannot be put at any random radius. It can be only put in specific orbits. And what are those orbits? Okay, the angular momentum of the lowest orbit is 1 H bar. The orbital angular momentum is quantized. Okay? So this is 1 H bar, 2 H bar, 3 H bar, and that's where those quantum numbers are. The n equal to 1 shell, n equal to 2 shell, and n equal to 3 shell. Okay. So this angular momentum quantity is a very important quantity. So here's another example. So our solar system was formed from a cloud like this. This cloud, our solar system was formed about 5 billion years ago. So you guys remember that solar system model that I bring in class, I brought in class, where the sun and the earth is about a foot away from there. Okay. So if the solar system was that big, it formed from a cloud as big as this campus, from Dunn Street to ISB to White Street. You guys understand? No? Okay. So it formed from a cloud that big. So this cloud was spinning slowly, and as it collapsed, just like an ice skater, this is spinning. Everything, the sun was spinning faster and so on. And then the planets are going around. Okay. But here's the deal. The angular momentum of this cloud this thing has remained constant for 5 billion years. And it'll remain constant forever. Okay? So I'll give you this one example and then we'll end. Okay. All right, so you guys saw this. Okay, so the force of Earth's gravity is trying to topple this top, and the effect is the top precesses. Okay, so if you have a torque acting on a spinning object, the object will precess. All right. Now, the Earth happens to be a spinning top. And it turns out that the gravity of the sun, if the Earth was a perfect sphere, then there would be no torque acting on Earth, and it would point like that forever. It would keep spinning like that forever. But the Earth is not a perfect sphere, and it turns out that the gravity of the sun and the moon are trying to topple the Earth. They exert a torque on that. So that should make the Earth's axis precess. Okay? And of course, we had made these observations. So the north, what is the North Star? It's just the star that's right above the axis. Okay? And you see, over thousands of years, the North Star has changed. So 5,000 years ago, that was the North Star. This is the North Star today. Okay? So you can calculate how long it takes for the Earth's axis to precess. And it turns out to be 26,000 years. Okay. So for instance, what does that mean? So if you came back to Earth 13,000 years from now, here in Florida, summer will be in December. Okay. All right. All right, this is a long story, so we won't, you guys can read about it. So we'll stop here, okay?